Okay, so let's look at what we have today. Hybridization. What is hybridization? Hybridization is the mixing of atomic orbitals to form a hybrid orbitals. Okay, now what do I necessarily mean in a layman understanding? Let me explain something. An orbital is a region in an atom or a space in an atom where electron resides. So anytime that particular atoms want to undergo bonding, right, its orbitals will come together so that it will be able to form a bond with the orbitals of the other element. All right, so that is why we say that hybridization is a mixing of atomic orbitals to form a hybrid orbitals. Hybridization can be seen in organic chemistry, general chemistry, right, and inorganic chemistry. But in today's class, we want to focus majorly on hybridization as seen in organic chemistry, right? And it's important for me to state that hybridization usually takes place at the central atom of every compound. And guess what? In organic compounds, carbon is always a central atom. So whenever we're talking about hybridization of organic compound, we're also referring to the hybridization of carbons. All right? So I'll say this is the mixing of atomic orbitals to form a new hybrid orbitals. All right? So, like I said, in organic compound, we are referring to hybridization of carbon. So when we say hybridization of carbon, we're also referring to hybridization as can be found in organic compounds. All right? So let's say types of hybridization of carbon. Remember, hybridization of carbon is actually found in organic compound because carbon is the central atom. So we have three major types of hybridization. Note what is formed after hybridization is called hybrid orbitals. So we have three of them. We have the first one, Sp3 hybrid orbital. We have the next one, Sp2. We have Sp3. So like I said, types of hybridization that is found in carbon, right, is equivalent to saying hybridization in organic chemistry because organic chemistry it's a chemistry of carbon and its derivatives. And all organic compounds must contain carbon, not just carbon. Carbon will also be the central atom, right? So if we actually said what is formed after hybridization is called hybrid orbitals. So we can say that we have three types of hybridization that can occur in organic chemistry, organic compounds, or we can say we have three types of hybrid orbitals that can be present in an organic compound. And the first one is Sp3 hybrid orbitals. The next one is Sp2, and the next one is Sp hybrid orbital. Now let me explain something. In the Sp3, do not forget that in terms of atomic orbitals, we have, these are the orbitals we have. We have S orbital, we have P orbital, we have D, and we have F orbital. Now, P orbital has three suborbitals. So when you say Sp3, what this simply means is that you're bringing one S and mixing it with 3P. So in total, in Sp3, you have 4 orbitals that is mixing to become Sp3. So this is hybrid, right? Coming together of this to form this. So in Sp3, we are mixing 1s and 3p. So if somebody asks you how many orbitals are present in Sp3 hybrid orbitals, it is 4 orbitals. Now, if I have Sp2, now this is obtained from mixing S and 2p. And once again, we are getting this 2p and 1s. We have sp2. And I have sp, s plus p. So take note of what I just said now. All right. So we're going to be looking at, I'm going to be defining each of them, their bond angles, where they can be found. And of course, I'll give us an example to see how you can identify a particular hybrid orbitals that could be present in a compound. Now, since we've seen the three types of hybrid orbitals that we have that are possible in organic chemistry, now the next step we have here, it's more or less like a characterization of these orbitals, right? The number of orbitals that is present in sp3. Remember, this is a hybrid orbitals. They are now seen together, right? Now, how many orbitals makes up sp3? That is what we're going to be looking at shortly. Now, what is the shape or the geometry? It's important for us to know that hybridization can also be used to determine the shape of an organic compound, right? Which we're going to be seeing shortly. Okay, so if a particular compound has a central atom having sp3 hybridization, right, we can actually tell the type of shape that compound is going to have. What is the bond angle for sp3 hybrid orbitals, and where can we find sp3 hybrid orbitals? So let's start. The number of orbitals here, we have 4, because this is actually obtained by mixing 3p plus 1s. The shape of sp3 is tetrahedral. The shape of sp3 hybrid orbital is tetrahedral, and it has a bond angle of 109.5 degrees. Now, which type of carbon, right? Which type of carbon atoms? Do not forget that these hybrid orbitals can actually be said to be that of carbon, because carbon is usually the central atom in all organic compounds. So these are actually hybridization of carbons, all right? So which type of carbon can actually have sp3 hybrid orbitals, class? Now, the type of carbon that is going to have sp3 hybrid orbitals are carbons that have 4 single bonds attached to it. 4 single bonds. For example, we have this. Anytime a carbon atom has 4 single bonds attached to it, that carbon is said to be sp3. Or we can simply say any carbon atom that has 4 atoms attached to it is said to be sp3, right? And where can we find those kind of atoms? In alkanes, in cycloalkanes. Do not forget that any carbon atom that has single bonds all through, no double bond, no triple bond, that particular carbon is sp3 hybridized carbon atom, all right? And where can we find those kind of compounds? In alkanes and in cycloalkanes. Now let's move down to sp2. Now, number of orbitals in sp2 is 3, because we have 2p and we have 1s. And what is the shape of this sp2? The shape of sp2 is trigonal planar or plane triangle. Now this has a bond angle of 120 degrees. Okay, so the next question is, where can we find carbon atom with sp2 hybridized orbital? Now listen, for sp3 we said the carbon atom has to have single bonds all through. Now for sp2, the carbon atom needs to have 1 double bond. In the case of sp2, the carbon needs to have a double bond, all right? So we have sp2 carbon needs to have at most 1 double bond. This is what we have here, and it must be attached to 3 atoms. So look at this. In the case of sp3, this guy is attached, this guy has 4 single bonds, right? And each of the bond is actually attached to a single atom. But in the case of sp2, this guy has 1 double bond, all right? The double bond is taking 2 bonds already, and this 2 bond is actually given to 1 atom. So the number of atoms here is 3. As we move down to sp, the number of atoms that sp carbon can hold will now be 2. Okay, so for sp2, the carbon needs to have a double bond. And where can we see that kind of carbon? In alkanes, right, carbon doubly bonded to carbon. In carbonyl group, carbon doubly bonded to oxygen. So the asterisk carbon here are the sp2 carbon because they are having double bond. Alright, this is alkene, carbon doubly bonded to another carbon, but this is a carbonyl which can be found in aldehydes or ketone, carbon doubly bonded to oxygen. Alright, now the third type of hybrid orbitals we have is sp. It has two hybrid orbitals and the shape of this guy is linear. Right, the bond angle is 180. And what is linear? What is sp? Sp is basically a carbon atom that has a triple bond. Now look at this. For sp hybridized carbon, right? Sp hybridized carbon are actually carbon atoms that are attached to two other atoms or two other substituents, or a carbon atom that has a triple bond. Now look at this. Now this is actually sp. This is attached to just two atoms. Let's say this is A and let's say this is B. Okay, let's call this sp hybridized carbon is carbon that has a triple bond. So this carbon, the two asterisk carbons are sp hybridized. Alright? Another example of sp hybridized is when a single carbon has two double bonds. Class, when a single carbon has two double bonds attached to it directly, that carbon becomes sp. Now this is not the same thing as saying this. This carbon here is only attached to a double bond, but in this case we have two double bonds, one on one side, one on the left hand side. So this is actually sp. This is sp, this is sp, this is sp2, and this is sp2. So do not mistake sp to sp2. sp carbon are carbon atoms that have triple bond attached to it, or a single carbon atom having two double bonds directly attached to it. Example of compound with this, we have alkynes. Alkynes, we have carbon triply bonded to another carbon. We have the next one, we have nitrile. Nitrile is when carbon is triply bonded to nitrogen. And then we have the next one, alene, carbon so these ones with asterisks, the ones with asterisks are the sp hybridized carbon. Alright, so this has a triple bond attached to it, this has a triple bond, then this carbon is having two double bonds directly attached to it. So this is an example of sp hybridized carbon. Alright, now so let's see how questions can be asked pertaining to this. Alright, so let's look at some few questions here. Now these are past questions from previous exams, and these questions are technical and tactical, so I would encourage us to pay close attention. Now the first one said, when numbered accordingly, what is the hybridization of the fourth carbon in one butene? So this is basically a very technical question. So you must be able to, interpret the name to the structure and then check the carbon number 4 to see if it is a single bond, a double bond, or a triple bonded carbon. Now let's go. Now one butene means 4 carbon, right? So let's say 1, 2, 3, 4. But this is butene. But means 4 carbon. In, E-N-E. Alright, this is E-N-E. Butene means there is a double bond at position number 1. So you start numbering this guy. This is 1, 2, 3, and 4. Alright, now this is position 1, so you put it here. Okay, so let's say 1, 2, 3, 4. So you can come here and then you add your hydrogen, the CH3, the CH2, the CH, and the CH2. Now they said when numbered accordingly, what is the hybridization of the fourth carbon? Now the fourth carbon is this guy. If you look at this fourth carbon, the fourth carbon does not have a double bond, neither does it have a triple bond. So anytime a carbon have single bonds all through, that carbon is going to be sp3, right? So this is the fourth carbon, and the fourth carbon has single bonds all through, and carbon with single bonds all through is sp3 hybridized. So the answer to that question is sp3 hybridized carbon. All right, now good. Now the next question says, underline the compound that bears the shortest carbon-carbon bond length among the following: cyclopentane, methane, heptane, 2,2-dimethylpentane. Now, when I gave us the table previously, like the table that contains the bond angle, the shape of different hybrid orbitals, I mistakenly, skipped the bond angle. So I had to present a new table this time around just for the bond angle. Now listen, carbon-carbon single bonds, that is sp3 hybrid carbons, have the longest bond length. In terms of bond length or bond distance, sp3 carbon have the longest. What do I mean? Carbon-carbon single bond, this is sp3, it has the longest. Now followed by carbon-carbon double bond, which is sp2. The one that have the shortest bond length is the sp. Now these figures I used here, these are not really the real figures, but nobody's really going to ask you for these figures. I'm just using these figures to actually tell us how the bond length differs. In terms of bond length, this is the longest and this is the shortest. Now sp2 is just intermediate between the longest and the shortest. So in this question here, what you really need to do is to find out the type of hybrid orbitals that are present in each of these compounds. Right? Once you found out the type of hybrid orbitals present in these compounds, you can now relate it to know whether it is sp2, sp, or sp3. Now look at this. If you could recall, when I gave us the table initially, I said sp3 can be found in alkanes or cycloalkanes. Right? Now this is alkane, this is cycloalkane. Cyclo, any compound that ends with N is sp3. Right? Alkanes ends with this. So any compound that ends with ane is an alkane, that is sp3 hybridized carbon. Right? So this is cyclopentane, methane, and 2,2-dimethylpentane. Class, this is sp3, this is also sp3, and this is also sp3. Now this is sp because this is ending with ine. Alkynes is carbon triply bonded to another carbon. So this sp, this alkyne, this is heptane. Heptane falls under alkynes. All right, and alkynes, their hybrid orbital is sp. And if you look at this, sp have the shortest bond length. So let's look at the question again. Underline the compound that bears the shortest carbon-carbon bond length amongst the following. Right? So the correct answer here is this guy, heptane, because this guy has the shortest bond length, because the hybrid orbital present here is sp. Why? Because this is heptane. Any compounds that ends with yne is an alkyne. Any ones that ends with ene is alkene, sp2, ane is alkane, sp3, yne is alkyne, sp. So since this compound ends with yne, it means that it is an alkynes, right? And alkynes have hybridization of sp, and sp have the shortest bond length. All right, okay. So the next question says, what is the value of the bond angle of carbon bonded to hydrogen found in methane. Class, these questions are very tactical, right? It's very simple question, but they are trying to play a fast one on you guys. Very simple. Carbon singly bonded to hydrogen. This is actually, they said, found in methane. Methane is an alkane. And remember what I told us, that all the carbons in alkanes are sp3 hybridized. For the fact that this guy do not have a double bond, right? That is enough for us to know that this is under sp3. And for the fact that they said it is methane, and I just told us now that any compound that ends with ane is an alkane, right? And alkanes, they have hybridization of sp3. And if you could remember, the bond angle for sp3 is 109.5 degrees. If it is sp2, it is 120. If it is sp, it is 180. Alright, so the carbon atom in alkanes, which is methane, falls under this category. So the value for this becomes 109.5 degrees. As simple as that. Alright, now let's look at the next one. They said, what type of hybrid orbitals are found in propyne? Propyne. Once again, propyne, what is this compound? Is ending with YNE, just like I told us previously. Any compound that ends with YNE is an alkynes, is an alkynes, and the hybridization of this guy is always sp. So what type of hybrid orbital is found in this? Propyne. But that is not enough, right? You need to draw out this compound, right? So that we can tell. They said, what type? So apparently, it's possible that we may have more than one type, all right? So let's see the type of carbon atoms that are present in this guy. Okay, so let's see, propyne is 1, 2, 3, right? Prop means 3 carbon. I means a triple bond. We have this. So the next thing we are going to do, we have CH3. We have this. So we have carbon A, carbon B, and carbon C. Class, how many types of carbon can we see here? Remember we said sp3 is mostly found in alkanes, right? sp2 can be found in alkenes. We said it can be found in alkanes. That does not mean that is the only hybrid orbitals that can be present in an alkanes. sp2 simply means that a carbon is having a double bond. What if in the same compound there is also another carbon that do not have a double bond but a single bond? So look at this. In this compound we have 3 carbons. Out of these 3 carbons, 2 of them, which is carbon A and B, are having triple bond. Carbon C is not having the triple bond. So you see that we have 2 types of carbons here. We have a triple bonded carbon twice, and we have a single bonded carbon. So these 2 triple bonded carbon are sp hybridized, and this carbon here, which do not have the triple bond nor double bond, is sp3. So it is possible for one compound to have more than one hybrid orbitals. It all boils down to the type of carbon that is present in that compound. If a compound has a carbon that has a triple bond, a double bond, and a single bond in the same compound, that means there's a possibility of us having sp3 hybrid orbitals, sp2 and sp. sp3, if there is a carbon that is singly bonded, do not have a double bond, do not have a triple bond. sp2 will have a carbon that has a double bond, and sp will have a carbon that has a triple bond. So in this compound here, we have 2 carbons with a triple bond, carbon A and carbon B, and we have a carbon with a single bond, that is carbon C. So that boils down to we having 2 types of hybrid orbitals, sp and sp3. sp for carbon A and B, and sp3 for carbon C. Alright? The next question says, what is the percentage of P character in sp3 hybridized carbon? I had to clean the board to actually solve this so that we understand. Now, first and foremost, you need to say percentage of p character equals to number of p all over total number of orbitals times 100. Okay, so they are asking us for percentage of p character in Sp3. So I'll say in Sp3, number of p is 3 because we have 3p here. Total number of orbitals is equals to 4. Why do we say 4? S is 1 plus 3, that is 4. So we'll now say, so therefore, percentage of p will be equals to number of p is 3. All over total number of orbitals is 4 times 100. This is going to give us 75%. Now with this pattern now, you can solve for any percentage of any character, be it S character or be it P character. Now, what if they had said percentage of S in Sp3? What if they had said percentage of S in Sp3? Would have said number of S orbital is equals to 3. Sorry, is equals to 1. Total orbitals in Sp3 is equals to 4. So therefore, percentage of S equals to S orbital is 1. Total orbital is 1 plus 3, that is 4 times 100. That is 25%. Alright? So the answer to this is 75%. Remember, this Sp3 you're seeing here can be changed from Sp3 to Sp2. If they change it from Sp3 to Sp2, simply means that number of p here will no longer be 3, but it will now be 2. So take note of the hybrid orbital in question. If they had said number of p character in Sp2, right? If they had said Sp2 and not Sp3, now this is what we would have gotten. We'll say number of p equals to 2. Total orbital is equals to 3. So percentage of p is equals to number of p, which is 2 all over 3 times 100. Right? You press your calculator and you get your answer. So that is how we solve for this particular question. Sp2 hybridized carbon has dash geometry with dash bond angle. If you could remember, take your mind back to the table I gave us earlier. Sp2 hybridized carbon has trigonal planar. Alright? So the geometry of Sp2, please, geometry is same thing as shape, equals to trigonal planar, and bond angle equals to 120. So that is how we actually, once you understand the concepts or the details, once you understand the concept or rudiments of hybridization, any question at all you come across, you'll be able to answer it. Alright? So please like our video, subscribe. Thank you.